All right, back recording here. So you guys have a paper with two different FRQs on it. Let me start by, let's look at the one that we're not going to do because we're probably going to run out of time and let's move on to other things. Right? There's one that has like two balls, one top of the other, and they're going to bounce off the ground. Do you guys see that one? Right. So just to run through the premise with you guys. Right? If you just have a single ball, I had you guys do a lab a few months ago where you dropped a single ball. What's the highest it can theoretically bounce back up to? Yeah, the height dropped from, right? The original height, right? Is there any way they could possibly bounce higher than that? So you guys see the setup here, right? So there's let's call it a ping pong ball on top of a tennis ball on top of a basketball. Now, if you run this, watch this. Pow! I saw the ping pong ball and the tennis ball fly off higher than they originally started, right? And the physics explanation would be, well, it's taking momentum from the basketball. So when it all collides with the ground, there's some momentum that's transferred from the basketball. Off they go. Right. So there's an FRQ that basically has you solve that. Right. So that's not the one that we're going to focus on today, though. Right. So switch over here. Right. I'll get you guys started. Right. Do you guys see one with a cannon and a marble? Cannon and a marble. Right. So I'll read this with you guys, then I'll give you guys most of the rest of the class to work on this. Right. So they're recommending 25 minutes. I'll put some time on the clock here pretty soon. Right. Students launch marbles mass m sub m, so mass of the marble is m sub m, from a toy cannon mass m sub c, right? So m sub c, mass of the cannon, right? The mass of the cannon is always greater than the mass of the marble. That's all good. Each time the marble is launched, the cannon slides backward before coming to rest, right? Oh, and probably that X that's shown right there, right? Oh, with the dash outline, which maybe you could have guessed just looking at the diagram before you even read that, right? Guys, if it slides to a stop, what do you know about the surface? There's what? Friction, right? Gotta be, right? Let's see if they mention that. Coefficient of kinetic friction between the cannon and the ground is mu. Oh, they spell it out for you. How about that? For each launch, the students use a new marble with a different mass. Ooh, so the mass of this marble is like variable. So they got different mass marbles going on, right? Launched at the same speed v relative to the ground, right? Now that right there, giving you guys maybe a hint, is a really weird detail. Okay? Would you naturally expect that? Like, if I gave you guys those launchers that we were using a few months back, and I gave you guys different mass balls, what would you naturally expect? Like the heavier the ball is going to fire the same speed, faster or slower? Should be slower, right? And there was, I think, a question I asked you guys on one of your quizzes a few months back. It was like, it assumed the same energy of the explosion, right? And you could run the numbers, and it's like, yeah, if it's the same like kinetic energy of explosion, you follow through with the math. Yeah, larger masses are not going to fire as fast, right? So I think they're making some huge simplification here. Every once in a while, AP does something like that, where I bet this is going to simplify something majorly down the road, right? So same mass marble, but somehow it's happening. They're getting the same blast speed of the marble, okay? Right? All right. The students record the distance x that the cannon slides backward each launch. Right? And then there's a series of questions. First question A, without manipulating equations, briefly describe what happens to the distance x the cannon slides backward as the mass of the marble is increased. Remember, let's assume that they're somehow all the same blast speed. Right? Explain your reasoning. Right? So they're recommending 25 minutes on this. Last class, it was around 19 minutes or so that students were like finishing up. So that's the time I'm going to put on the clock. You guys go ahead, see if you can do the whole FRQ in that time, and then we'll take about the last few minutes of class to start going over the answer, and we'll take a Friday to finish this. Okay, so there you go. Time's ticking. Yeah, 3, 2, 1. There's a good amount of time there. Looks like you guys are about finished with that. So let's go through this. Okay. So question A, without manipulating equations, briefly describe what happens to the distance x that the cannon slides backward with the increasing mass of the marble. Right? What did you guys see? Let me see, quick show of hands. Right. So as you increase the mass of the marble, again, somehow assuming the same blast velocity. Right. So with increasing mass of marble, what happens to x? Does x also increase, decrease, or stay the same? How do you guys say x increases with the increasing mass of marble? Increase. Who says that? Oh, all right. Is that everybody? All right. I think that's correct. All right, let's see. How did they score that? Oh, and then you had to explain your reasoning. They came up with 2 points for this. 2 points. Okay. And this is split over 2 different pages, so see if I can put it out here. Okay. So 2 point. First point, there's an either or. So you could have said something like this, something about conservation of momentum to indicate that the larger marble mass means a larger cannon speed, right? Because a larger marble mass times this, same velocity or whatever would be more and more momentum units to the right. Okay. Guys, how many units of momentum just everything sitting there before it blasts? 0, right? There's 0 momentum ever in the system, right? So mv to the right has to balance with mv to the left, right? So some did that, right? Or they got a big old or here, right? Maybe you said something a little different. Okay. So here's the other thing you could have said to also get the same first point. For using a combination of Newton's third law leading to Newton's second law to indicate a larger marble mass means a larger cannon speed, right? What was Newton's third law? Something about what? Equal and opposite forces, right? So guys, when that cannon blasts that cannonball, right? Remember the mass of the cannon is greater than the marble, I should have said, right? Because which object has a greater force acting on it, the marble or the cannon? The same force, because that's Newton's third law. So if you said that followed by what does Newton's second law say? Acceleration is caused by a net force acting on a mass, right? So if it's the same force on different masses, then okay, so different accelerations, right? But anyway, all right, so you guys get there? Okay. Okay, and here's the second point, right? For explaining why a larger cannon's speed results in a greater sliding distance. So if you somehow mention that, okay? Right, so you guys get there? Okay. Right, then they came up with an equation for that. Oh, actually, pause right here. Right, let's look at their example response real fast. Example response. Okay. They've got 2. The initial momentum of the marble cannon system is 0, so it will also be 0 after the marble is launched. A greater marble mass means that the backward cannon speed is also greater, since the acceleration due to friction is the same regardless of the cannon speed, right? Coefficient of friction is the same, acceleration is the same, it's slow down rate, right? Greater cannon speed means that the cannon will slide a greater distance, right? Or when the marble is in the cannon, the force on the marble has the same magnitude as the force in the cannon. That's Newton's third law. If the final speed of the marble is the same each time, but the mass of the marble is increasing, that means the net force on the marble must also have been larger. According to Newton's second law, therefore the force on the cannon also must have been larger. Right? The force of friction remains constant, so the cannon has a larger final speed, resulting in a larger sliding distance. Something like that. All right, so you guys get there? All right, here's the first 2 points. All right, question B. Students find the following equation on the internet to describe distance x that the cannon slides backward. So they're making this claim. The sliding distance x is equal to mass of the marble squared, blast speed of the marble squared, all divided by 2 times gravity field times coefficient of friction times mass of the cannon squared. Right? Now, maybe that's true, maybe not. Whether the equation is correct or not is would be consistent with your prediction in part A. Briefly justify your answer. Okay. Oh, so I guess relationship here is the larger marble mass, all else the same, is going to correspond to larger distance x, right? Actually, what exactly does this equation say with that relationship? Like, guys, if you triple the mass of the marble, according to this equation, the sliding distance increases by a factor of what? 9. Right? I got another question for you guys before we look at the answer key here. Is that equation actually true based on the premise of like the same blast speed for the marble? Right? Oh, did you guys try that out and see, is that equation actually true? Right? Let me see, show of hands, what do you guys think? How many guys think that, yeah, like given the premise that they laid out, that equation actually does check out? It is true. That is a true equation. How many guys say that? All right. Yeah, I think so too, because I did the math. So here's momentum is being conserved, right? For a blast, think like an explosion. It starts off 0 momentum was ever in the system. So here's cannon, marble. Now the marble, velocity I just called V, just like they did, right? So it's that. Everything else has subscripts on it, right? Now, what is the post-blast speed of the cannon? Right, and how does that relate to the sliding distance? Well, here's where in this cloud bubble, I've got this kinematic motion. Here's the third kinematic formula, the time-independent one, right? And okay, it's eventually going to slide to a stop. That's why I have final velocity 0. This is the cannon slowing to stop. The acceleration I called coefficient of friction times gravity field. There's a little bit of substitution proof there that I kind of skipped a little bit, but you guys have seen that plenty of times, right? And then what? Okay, so if you solve for the post blast speed of the cannon, you get this expression in terms of its sliding distance to a stomp, right? So we take that and substitute that right there. Right? Now it looks like this. So this conservation momentum with that substitution I just made from kinematic, right? And then let's suppose I go solve for x. So algebra, algebra, algebra. Here's what x ends up being. It ends up being exactly what they said those students found on the internet. Okay. So yeah, it does check out. Does check out. Okay. Let's see how they. Oh, actually, that was gonna be like 5 seconds. All right. So yeah, hold on to that FRQ. We'll finish scoring this tomorrow. Now take us to the weekend. Oh yeah. All right. You guys have a great night. Enjoy leap day.